Hello, this is Dr. Padma Nair, and we will be talking about chapter 1, structure and bonding today. Before we move on to the details of the structure and bonding, let's just quickly understand what the importance of organic chemistry. So what is organic chemistry? Now, organic chemistry occupies a central role in the world around us. The food that we eat, the clothes that we wear are all made up of organic compounds. Our ability to smell, see colors is also a result of organic compounds. Our bodies are made up of mostly organic compounds like the DNA, RNA, proteins, etc. The response of our bodies to pharmaceutical drugs are a result of reactions guided by the principles of organic chemistry. So a deep understanding of organic chemistry helps us to design new drugs that fight diseases and improve the quality of life. Now here in this slide here, you can see examples of some common organic compounds which are well-known pharmaceutical drugs too. Common names like Vioxx and Lipitor, OxyContin, cholesterol, etc. Um, Even though the structures may not make a lot of sense to you right now, but as we go through this semester, you will learn about how to draw organic compound structures and what do these shapes of these molecules represent and their importance. Now look at this one. This is one of the um, drugs called remdesivir, and maybe some of you all have heard this on the news regarding the being studied as one of the treatments for COVID-19. So if you want to read about this drug, you can go to some of the known websites and look up at the structure of the compound and read more about it, about its mechanism of action, etc. Anyway, the goals of this chapter are that by the end of this once you finish studying this chapter, you should be able to predict ground state electronic configuration of atoms, be able to draw the Lewis dot structures of simple compounds, be able to predict and also describe hybridization of bonds in simple organic molecules, be able to predict the bond angles and shapes of molecules, as well as draw the condensed and skeletal structures of organic molecules. Okay, so most of these topics here, the first four of them are from your general chemistry review. So if you have notes from your general chemistry, especially Chem 151, you may be able to look this up and try to remember the matter that you studied under these topics. This last part is kind of a little bit new, so we will be working a little more time on how to draw condensed and skeletal structures. However, in this particular video, which is around 10-15 minutes, I'm going to be talking about a little bit about the structure of atom and also how to predict the ground state electronic configuration of atoms. So if you look at this is a periodic table, and we have highlighted a few elements here, which are the most common elements that are found in organic compounds. And out of that, carbon is the main element that is found in almost all the organic compounds, right? So it is called as the study of carbon compounds. Now, why is carbon so special? About 90% or more of the 30 million chemical compounds that are known, they actually contain carbon. So if you look at the position of carbon on the periodic table, it is actually a group 4A element with 4 valence electrons, and it forms 4 covalent bonds. Let's start a little bit review about the structure of atom. You all know that the atom consists of a very dense nucleus, which is made up of the protons and neutrons, and it is surrounded by negatively charged electrons. And according to the quantum mechanics theory, the electrons are present around the nucleus in the form of a cloud. We call it as an electron cloud. And this is how we represent a atom with the nucleus at the center containing the protons and the neutrons, and the surrounding space, which is occupied by orbiting electrons. Now, what is an atomic orbital? right? We should think of atomic orbital as a region of space that can be occupied by electron density. So we sometimes call this also as an electron cloud. So according to quantum mechanics, the electron energy is represented by a wave equation which can be solved to given a series of solutions which are called as wave function. And each wave function is an orbital which is represented by psi. A plot of psi which describes the electron is most likely to be, is where the electron is most likely to be, and actually psi square is what describes the probability of finding an electron in a certain area. Okay, so we call this orbital as the most probable area where you can actually find the electron. Again, recalling from general chemistry, you know that there are four kinds of orbitals. Again, what is an orbital? It is the region around the nucleus where the probability of finding the electrons is the maximum, right? So based on the quantum mechanics theory, and also by knowing the several quantum numbers, etc., you should be able to predict how many electrons can be um, placed in each of the different energy levels. So the four different kinds of orbitals are the s orbitals, the p orbitals, the d orbitals, and also the f orbitals. Here I have not drawn the f orbitals, but there are four main orbitals which you need to know about. The s orbitals are spherically symmetrical around the three axes. The p orbitals are dumbbell shaped and it has the nucleus at the middle. The d orbitals are elongated and dumbbell shaped. They have four lobes in this manner, right? And then f orbital is more complex, and you can take a look at it, the shape of it in your textbook. Now, s orbital is spherically symmetrical, and there is only one s orbital that's possible, which because the orientation of it is same on around all the three axes. However, in the p orbitals, you have three types of p orbitals. They're denoted as px, py, and pz. They are called as px, py, and pz based on where the probability of finding the electrons is the most. So if the probability of finding the electrons is maximum on the x-axis, we call it as a px orbital. If it is on the y-axis, we call it as py, and on the z-axis, it's called as a pz. Now there is also a node here, which is the region of no electron density. Now recall again from general chemistry that how you can arrange the different electrons in the different orbitals based on their increasing size and energy. They are based on, the filling up of electrons is done based on three different rules. So before that, you should also know that the 1s orbital, the first shell contains 1s orbital, is denoted by the symbol 1s, and it can hold only 2 electrons. Second shell contains a 2s and a 2p. The third shell contains a 3s, a 3p, and a 3d. And each of these orbitals can take a maximum of 2 electrons. And the way you can arrange them is based on the rules, which is first rule is the Aufbau principle, where the lowest energy orbital gets filled first. So the easiest way to do this is to write it down in such a manner that you can draw arrows which help us to guide which orbitals are lower in energy and which one are higher in energy. So the order goes in this way, that first it is 1s, then 2s, then 2p, then 3s, then 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and so on. So if you want to write it down in the increasing energy orbitals, so here is, so if you have the energy increasing, right? So you can go from, so we have 1s, then 2s, then 2p, 3s, 3p, right? And then it's not 3d, it's actually 4s, and then comes 3d, and then 4p, then 5s, and then 4d, etc. Okay, so you just need to follow these arrows. So 1s, go back, then 2s, then go back, then 2p, 3s, go back, 3p, 4s, and then 3d, 4p, 5s, etc. Okay, so keep this rule in mind while filling up the electrons in the different energy levels. Second is the Pauli's exclusion principle, that you can only have 2 electrons in each orbital and they should have opposite spins. So in other words, if you have an orbital with electrons with similar spins, this is not allowed according to the Pauli's exclusion principle. So you need to be drawing it in opposite spins. When 2 electrons occupy an orbital, they must be of opposite spins. The third and rule which helps you to fill up electrons in different energy levels is the Hund's rule, which states that if 2 or more empty orbitals of equal energy are available, then the electrons occupy each with spins parallel until all orbitals have 1 electron. So that means, say for example, if you have 4 electrons to be filled in a 2p orbital, right? So you will have to first fill up individually. Okay, so say for example, I have this as my 2p orbital, and you have to fill up 4 electrons. Okay, so this is my 2p. Just assuming that my 2s and my 1s are completely filled. Remember, each orbital can take a maximum of 2 electrons. Okay, and now 2p, you have 3 of them, right? They are the 2px, so let's call this as 2px, this is 2py, and this is 2pz. And each of them can take 2 electrons. Okay, so that means you can take a maximum of 6 electrons in 2p. But say, for example, I have only 4 electrons which I need to fill up. So how will you go? You'll fill each orbital with 1, and then fill the 4th electron you can pair up the 4th electron in this orbital. Okay, so I use this half arrows. You can use that, or you can write full arrows. It doesn't matter. For simplicity's sake, we use this half arrow, so you can do it either way, right? So keep these rules in mind, the 3 rules of Pauli's and Hund's rule, in order to write down the electronic configuration. So I would ask you to please go ahead and review topics before this regarding atomic structure, quantum numbers, what are the allowed quantum numbers for each of these energy shells, etc., before you start with electronic configurations. Okay, but anyway, let's practice a few here. Now look at this one. Here it's showing a few elements and their electronic configurations. So hydrogen is 1s. There is only 1 electron for hydrogen. So you need to know the atomic number of each of these elements before you start writing the electronic configuration. So hydrogen is 1, so it goes 1s1. Carbon has 6, so you have to arrange it in their increasing energy level. So 1s, 2s, 2p. So the 6 electrons will be filled as 1 and 2, 3, 4, and 5, 6. Okay. Phosphorus is 15, and this is how you fill it. Now, here it's a learning check that which one of the following represents the ground state electronic configuration of carbon. Now, what do we mean by ground state? That means when in a normal state, like carbon, if you excite it, that if you give it some energy, then electrons can move from lower to higher orbitals, right? So that is what is an excited state. However, we are talking about normal ground state of carbon, and what would be the electronic configuration. So you know that carbon is 6, right? Just like we saw in the slide before. And according to the off-pause rule, the 1s should be filled first. This is my 1s, and then my 2s, and then in 2p I have 3. Now why do I write them one next to each other? Because they are all of the same energy. And we actually call them as degenerate orbitals. Okay, so orbitals with same energy are called as degenerate orbitals. And this is the case with our 2p. So I have 1s, 2s, 2p. We have 6 electrons, so you start from filling up the 1s, 1, 2, 3, 4, and then 5, 6. We have to go here and check which one is correct. So we have 1s, so we can do the elimination. This is not correct because we know that 1 is 1. That cannot be possible, right? Then out of these, we have 1s2, 2s2, then 2p2. So 1s2, 2s2, 2px2, no, because that is not according to our Hund's rule. We need to fill it up individually before we start pairing. So 1s2, 2s2, 2px1, 2py1. That seems to be correct. And I would choose this one as my correct answer. So let's check it. Yes, it's 1s2, 2s2, 2px1, 2py1, and 2p0. Okay. Okay. So here we are going to practice writing the electronic configuration of a few more species. Some are with a positive charge, like this carbon with a positive charge, or you can have neutral atoms like nitrogen, sulfur, phosphorus. Okay. So this we represented as N. This we represent as C plus because it's a positive charge, sulfur S, and phosphorus P. We can look up at the atomic numbers from the periodic table. Nitrogen is 7. Carbon is 6, but remember this is a positively charged carbon, so it has lost electron. So you should actually have 6 minus 1, that equals to 5. Sulfur is 16, and phosphorus is 15. So you can write this as 1s2, 2s2, 2p, how many? 3, right? Because 7 electrons. Now carbon will be 1s2, 2s2, 2p1 because you have lost 1 electron, so it's 5 here. Sulfur will be 1s2, 2s2, 2p6, 3s2, 3p4. And phosphorus will be 1s2, 2s2, 2p6, 3s2, 3p3. Here is the key to all of that. Okay, so let's practice writing the electronic configuration of a few more elements. Let's pick chlorine as our example. Now, if you look at chlorine has electronic the atomic number is 17. So chlorine is 17. So you can write this as 1s2, 2s2, 2p6, 3s2, and 3p5. Now again, remember this has to be written in the increasing order of the energy, and according to the Aufbau's principle. 1s is the lowest, then the 2s, then the 2p, then the 3s, then 3p, then actually 4s, 3d, 4p, so on. Okay, so these arrows here guide you to write down the electronic configuration in the increasing energy levels. Okay, so 1s, then 2s, then 2p, then 3s, 3p, 4s, and then 3d, 4p, 5s, so on. Okay. Another example, so the other way of writing this would be where you can use this as your core electrons represented by the noble gas, which comes right before it. Neon covers 10 electrons, and then you can write it as 3s2, 3p5, which are your valence electrons. So this is called as the condensed electronic configuration, and this is the expanded one. So you can do it either way, but you will figure out that doing the condensed one makes it much more easier to write down the electronic configuration. Let's take another example. How about silicon now, right? Silicon is 14, belongs to the carbon family. 14 is the atomic number of silicon. Here it is. And again, you can do the expanded where you write down 1s2, 2s2, 2p6, 3s2, 3p2 here, right? So that covers 14 electrons. Or you can represent this by the noble gas neon, which covers the core electrons, and then you have 3s2, 3p2 as your valence electrons. Okay? So hopefully this kind of helps you to understand how to write down electronic configurations, and then you should now be able to practice from the textbook. End of the chapter, EOC stands for end of the chapter, and I have provided some suggested homework problems, so maybe working on that will help you to understand this chapter. Okay. In the next video, we'll talk about drawing Lewis dot structures.